This video will cover the topic limits at infinity. So let's consider first this function we see shown here graphed, f of x equals 3x squared over x squared plus 1. And we are asked to find the limit as x approaches infinity of this function. What could we mean when we say we want to see the limit as x approaches infinity? Well, we can't approach it like other limits where we looked at the left-hand side and the right-hand side. There is no other side of infinity. So the idea we want to think about is what happens as this goes towards infinity, or if it said negative infinity, what happens as the graph heads towards negative infinity? One idea you can think of is what is the end behavior? We are looking for the end behavior of this function, be it the negative infinity or infinity kind of idea here. So if we look at this function, what happens with the graph as it approaches infinity? Well, it tends to level off. We can see that it's sort of leveling off. And I know it's just part of the graph. We only are going, to like 12 or 14 right here. But this graph keeps going in this pattern. To the right and the left. It seems to level off, and it's looking to level off right around the y value of 3. So we could say it levels off around the y value, y equals 3. And that seems to be what is happening, the end behavior of this function. So let's look at a definition about that leveling off. So a line y equals L is a horizontal asymptote. So horizontal asymptote of the graph of a function when either the limit as x approaches negative infinity of the function equals that L. Remember, we're saying that L is a horizontal asymptote. If the limit as we approach negative infinity is L, or the limit as we approach positive infinity of the function is L. So that horizontal asymptote is the kind of leveling off that we see. And usually we draw it in kind of as a dotted line. So there's that horizontal asymptote. Okay. So we have a theorem about these limits as we approach infinity when we're talking about some. So let's look at that. So our theorem, if r is a positive rational number and c is any real number, then the limit as we approach infinity of c over x to the r is 0. So think about what that is saying here. C is some constant, and r has to be positive and rational. So x to some positive rational power. If we have a constant over x to some power, positive and rational, it's going to approach 0 or the function will approach 0 as x approaches infinity. It's going to level off towards 0. And you can kind of think about that denominator is going to dominate that constant. That constant is going to stay some finite number, some constant number, and this is going to get larger and larger and larger. Also, if our x to the r is defined when x is less than 0, kind of what you want to think about here is, if we're taking a square root, x to the 1/2, we can't go towards negative infinity. So just when it's defined, as we approach negative infinity, it's going to go towards 0 as well. So let's find some limits. Okay. So as I look at this, I kind of have two pieces, and one of our properties of limits says that we can look at them individually. So I'm going to say that this is the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 5 over x cubed. Now, this first part, the limit is x approaches infinity of 4. Remember, 4 is just a horizontal line at y equals 4. So that's always 4. So that's a 4. Bring down my minus. And now I want to look at this part. The limit is x approaches infinity of 5 over x cubed. Well, that's like my theorem just told me. If I have a constant on top and x to a positive rational power on the bottom, then this is going to head towards 0. Kind of what you can think about is we're plugging in numbers like heading towards infinity. So these are giant, giant numbers that then I'm cubing. Well, 5 over some giant, giant number cubed is heading towards 0. So that's 0. And then 4 minus 0 is 4. So that limit is 4. All right, so let's look at this next one. The limit as x approaches infinity of this rational function, 2x minus 5 over 3x squared plus 1. Well, the only thing I really have to go by right now is this theorem that I just looked at. So kind of what I need is I need some constants over a x to a positive rational number. So I'm going to play around with some algebra to make that happen using that theorem above. So what I'm going to do, so the limit as x approaches infinity, I'm going to take each piece of the top and each piece of the bottom and divide them all by x squared. And why am I choosing x squared? What I'm doing is I'm looking at the denominator and choosing its highest power. So I'm going to have 2x over x squared minus 5 over x squared over 3x squared over x squared plus 1 over x squared. And notice a lot of this can simplify, so let's do that real quick. So the limit as x approaches infinity. 2x over x squared, well, that's 2 over x. 5 over x squared, I can't do anything. 3x squared over x squared is a 3. And then 1 over x squared, that just stays. And now notice I have it in the form that my theorem lets me use. It constants over x to powers. Well, except for this guy, but he's a 3. He's just a constant kind of like this, so that'll be easy to deal with. So what do I get? Well, on the top as x approaches infinity, 2 over x will go to 0. 5 over x squared will go to 0. 3 is going to go to 3, and 1 over x squared is going to go to 0. So I have 0 over 3 or 0. So this limit is 0. All right, so let's look at this next one. Notice it's very similar to the one we just did. We've just kind of changed the powers up a little bit. The top is now an x squared as its degree highest power there, where that one was just a plain old x. But we're going to do the same idea. We're going to take the limit as x approaches 0. Oh, sorry, excuse me. X approaches infinity. We're approaching infinity now. Of each of this. Again, we're going to divide each one through by x squared, and we're choosing x squared because of the denominator's highest power. So this is 2x squared over x squared minus 5 over x squared over 3x squared over x squared plus 1 over x squared. And let's simplify all that before we evaluate it. See, that's going to be a 2 minus 5 over x squared over 3 plus 1 over x squared. And now as we approach infinity, that constant 2 will go to 2. The 5 over x squared will go to 0. 3 will go to 3. The 1 over x squared will go to 0. So this one goes to 2/3. All right, let's look at another example. It's going to be kind of similar to the ones we just did, but now what we've done is that highest power on the top is now a cube. So we've done the first power, second power, and now we're doing a cube. All right, so I'm going to do that same method. I'm going to divide through by the highest power of my denominator to see if that helps me sort of clean things up a little bit. So what do I get? I have the limit as x approaches infinity of 2x cubed over x squared minus 5 over x squared over 3x squared over x squared plus 1 over x squared. Clean some of this up now. I end up with a 2x minus 5 over x squared over 3 plus 1 over x squared. And now let's sort of think about what's happening here. This one's going to go to 0, and this one's going to go to 0. They're not really going to account for much. But now if I look right here, this 2x and the 3, okay? The 3 is just going to go to 3, some constant, right? So I guess I know my denominator is going to some constant. It's going towards 3 plus 0. But my numerator, what is happening there? Well, as we approach infinity, think about plugging in very, very large numbers here. 2 times a million, 2 times a billion, 2 times a trillion. And then those are even not large enough to really consider. So this is going to be a very, 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 very huge number. So it's heading towards infinity. So what we can kind of think about is the top is outrunning the bottom. The top is dominating my denominator here. So this thing is heading towards infinity. Okay. So what we've just done is actually going to provide us some shortcuts to find these from now on. So let's sort of investigate this number 2, 3, and 4 and see if we can find some patterns. On number 2, what did we notice? What's kind of the important thing here is the degree of the numerator is less than the degree of the denominator. And remember, the degree means the highest power that's happening there. So think about what's going on. If your denominator is really big and way outrunning your numerator, and think about, we're heading towards infinity. It's not like we're plugging in 1 and 2. You know, if we were plugging in very small numbers, 2x and 3x squared may be kind of similar. But as we're plugging in just infinitely large numbers, that denominator is way outrunning the numerator. That's causing it to go towards 0. The entire fraction is heading towards 0. When we look at the middle one, the degree of my numerator is the same thing as the degree of my denominator. And think about what's happening there. They're growing at roughly the same rate. Now, as you're talking about approaching things like infinity, this -5 and this +1 like really aren't that big of a deal. Each piece, the numerator and the denominator, are going to be driven by their highest power. Okay? So both of these are growing at roughly the same rate, x squared, x squared. However, we're going to look at the ratio of their coefficients, 2 to 3. This bottom one is growing a little faster, 3x squared as compared to 2x squared. So when that happens, when your numerator and denominator have the same degree, you're going to look at the ratio of their coefficients, 2 over 3. Notice, our answer was kind of hiding in right there. And then on this last one, what's happening? The degree of the numerator is now greater than the degree of the denominator. Okay, so now which one is outrunning? Well, the top is way faster than the bottom now, right? That x cubed is running way faster than that x squared. The top of the fraction is outrunning the bottom. That's heading towards infinity. Now, when you get the infinity, again, we need to be careful. If we were approaching negative infinity, we'd have to consider that, the positive or the negative situation here. But it's approaching something infinite, and then we have to figure out positive or negative. So kind of what this boils down to is all of this that we did here and here and here, where we went through, dividing everything through by the highest power in the denominator. What it boils down to is we can just get these three kind of rules out of it. So let's kind of summarize that of finding these limits for the rational functions. So our first thing is if the degree of the numerator is less than the degree of the denominator, denominator. This is going to imply that the limit is 0. Again, why? The denominator is outrunning it. If you have a fraction with a tiny numerator and a gigantic denominator, it's heading towards 0. All right, number 2. If the degrees equal each other. So if the degree of the numerator equals the degree of the denominator, what is this going to apply? Well, this is the limit is the ratio of the leading coefficients. Why? Well, if their degrees are the same, they're growing at roughly the same rate, so we just compare their leading coefficients. Okay, and then number 3. If the degree of the numerator is greater than the degree of the denominator, now that numerator is very big. It's kind of like a top-heavy fraction. The top is very, very large compared to the denominator. So now this limit is approaching something infinite. we'll say positive or negative infinity, and we'll have to check to see which one. Okay. All right. With these new rules in mind, let's do these following limits. Okay. So now we don't have to go through all the dividing out. We'll just use these rules. All right. So my limit is approaching infinity of 2x over x minus 1. What's happening here? The degree of the numerator is the same as the degree of the denominator, right? They match. Since they match, I look at the leading coefficients. So it will be 2 over 1. Technically, that x has a 1 with it, right? So 2. This limit is 2. Okay? All right, number 2. We want to look at the limit as we approach negative infinity of x cubed. And it may help to think, okay, well, that's x cubed over 1 to visualize what's going on here. And in this case, my degree of my numerator is larger than my degree of the denominator, right? I could kind of assume this is the same thing as x cubed over x to the 0, right? Because x to the 0 is the same thing as 1. I can think of it like that to help me compare. All right, so since the numerator is greater than the denominator, this implies positive or negative infinity, and I have to think a minute to figure out which one. So let's figure out what's going on. Well, the denominator is going to be 1. I'm not worried about that. My numerator, though, think about what happens. You have some very, very large negative number, negative a million, negative a trillion, negative a billion. What is happening if you were to cube that? Well, cubing a negative number is still going to be negative. So it will be a negative large number. So negative divided by positive, this is going towards negative infinity. Which hopefully, maybe you could have thought about this graphically as well to back up your answer. What does the graph of x cubed look like? Well, if we do a quick little sketch, x cubed, remember, is kind of this guy. Okay, so as we approach negative infinity, what is that saying? As x's go this direction towards negative infinity, what is our graph doing? Well, it's going down forever. So that visual helps make us feel good about our answer that we found algebra or using calculus. All right, let's look at this next one. The limit as we approach infinity of 9 minus x squared plus 4x cubed over 3x squared minus 7. So again, what do we want to do? We want to check our degrees of the numerator and the denominator. So the degree of our numerator here, notice the degree of my numerator it's a cubic function. So this is one thing I want to make sure you're paying attention to. Don't always assume that these are written in order. Don't just look at the first ones always. Make sure you actually look for the highest power. So here, the degree of my numerator is actually greater than the degree of my denominator. Okay, it's greater than my degree of the denominator. So what is that telling me? It's either positive or negative infinity. So let's do a little analysis to think about what's going on. So I'm plugging in, we're plugging in really large positive numbers, right? Because I'm approaching infinity. And the top sort of is going to be 4x cubed. Well, a positive 4 times a positive number cubed, the top is positive. And then the bottom is really just that 3x squared I need to pay attention to. That's what's driving everything. A positive number times a positive number squared is positive. So this one is going towards positive infinity. All right, let's look at number 4 up here. The limit as we approach infinity of 2x plus 3 over the square root of x squared minus x. So this one looks a little different because we're seeing the square root pop in. So we need to be careful, but we can kind of analyze it the same idea. Remember, the whole idea here is the highest power is what dominates these graphs, okay? The highest power, because we're heading towards infinity. We've got these gigantic large numbers. It's really the highest power. This is what matters, is what drives the functions. So what I can think about, this doesn't equal, but, it's about the same as the limit as we approach infinity. Well, the the highest thing is the 2x. And the bottom, we see that square root of x squared. I don't have to really worry about this minus x too much because, again, it's that highest power that's driving the function. So what's kind of going on here? I have 2x. Well, what's the square root of x squared? Well, that would be just an x. So these are actually having matching powers here. It's 2x over x, right? That's kind of the idea. That's what's going on here. So since they match, I can think the degree of the numerator equals the degree of the denominator. Since they match, I can say that they just go to 2 over 1 or 2. Okay. All right, so let's look at this next one. Limit as we approach negative infinity. So we know we might have to think of things a little differently now because we're approaching negative infinity. So let's keep that in the back of our mind. Of negative x squared plus 6 over x cubed minus x squared plus 1. So the top is x squared and the bottom is x cubed. So the degree of the numerator is less than the degree of the denominator. So what happens there, if the degree of the numerator is smaller, that means the bottom is outrunning. So if you have a fraction with a very gigantic denominator and a numerator that can't keep up, remember this is the situation where we're heading to 0. Okay. And let's look at one more down here. We're going to sort of do that same analysis as we did as number 4. We've got this 1/3 power thing happening, but that's okay. Remember, as we approach infinity, we're only really concerned about that highest power. What is going on there? What is driving the functions? So I can sort of think about this. Well, the top is kind of like x, and the bottom, well, we're not going to do this officially, but it's kind of like an x squared, but that squared is going to have the 1/3 power. Again, these don't equal. What I'm writing is not equal to this original function, but it kind of behaves the same way. So what we can think about is this is like x over x to the 2/3. And I can say x to the first to sort of help me compare. What's going on now, the degree of our numerator is bigger than the degree of our denominator, right? Because 1 is bigger than 2/3. If the top is outgrowing the bottom, we know something infinite is happening, right? We got to figure out which one. So positive or negative infinity. Well, I'm approaching positive infinity, and I have just x on the top and x to the 2/3 on the bottom, so I don't have any negatives to really worry about at all. So I would choose positive infinity.